All right, let's see. Big O, we'll talk about that. Here's a good one. Why are we revisiting arrays and what are implications for our code? Why are we revisiting arrays? Well, the answer to that question is that arrays are something that you use over and over and over in your code. They're probably the most commonly used data structure. And second is probably hash tables, which are going over second. And now we did them in Python. We looked at that. You've probably done them in Swift and JavaScript. But now that you know C, now that you have exposure to C, we can really get into them and see what's going on under the hood. And arrays, on one hand, are extremely simple, but on the other hand, can be pretty complicated, which you may have noticed from the video. So, and the example that I gave at the end, where if you add an element to the front, it's big O of n, and if you add it to the back, it's big O of 1. So that's linear versus constant. So if you don't know how arrays work underneath the hood, it can have serious implications on the performance of your code. So for something used that commonly, it's important we're going to revisit it. How does JavaScript calculate each element address in the array if the elements are each different types? That's a great question, and we'll get to that. The short answer is pointers. Each pointer is the same size, but it can point to different things. And now that you know C, you know what we're talking about when I say that it's a pointer. But we'll get more into that in the second half. There are instances where you don't have to declare the size of an array. I think that's in like JavaScript or Python or other high-level languages, and that's what you will be implementing for your homework. You will be implementing resizing arrays, so you'll understand the answer to that. Similar question. What's the largest number you can represent in 4 bytes? So that's 2 to the 32nd power if you're doing unsigned int, which is approximately 4 billion. A little deeper recap on big O of n measurements. We'll do a lot more big O coming up. Inserting elements in the beginning, we'll look at that. So inserting an element to the beginning list is not big O of n squared itself, it's big O of n. But since in the example, when we had it in the loop, there's an n inside of a for loop, which is n squared. But we'll go over that again in the second half. Does the block of memory have to be continuous? Yes, it does. Can we not have the last byte of the memory be a pointer to another block where the array can continue? Are you confusing this with linked list? Yes, that would be a linked list. The reason that we don't do that is because that would mean in order to get to, say, the 100th element, you would have to traverse the linked list, or you would have to go through the links, right? Which would not be constant time. So that's why we don't do that. And we'll go over why visiting an index in the array is constant time also. Adding an element to the end of an array is, again, adding an element. I hope this example didn't confuse you. Adding an element to the end of an array is big O of 1, but in the example, which I have actually up here, I brought my slides just in case. Whoop, close. In this example I gave here, this whole function, you see we have a for loop. A for loop is O of n, right? And then you have a constant in here. So this whole function is O of n. When you're inserting to the front, that's O of n inside of this O of n. So that's a for loop inside of a for loop. Now you can't see the second for loop because it's hidden, right? Like x.insert, this looks like big O of 1, but actually there's a for loop inside since you have to go through each element in the array and scoot everything over by 1. So that's a for loop in a for loop, which gives us n squared. But the operation itself is just n. It's the for loop that gives us that extra n factor. Let's see. What is the big O of adding an element to the end or beginning of an array in JavaScript? This is exactly how it works in JavaScript. Same as Python. Arrays are the same in Swift. Same in all of these high-level languages. This is how arrays work. in high-level languages. When you look in C, none of that stuff is done for you. You have to do it all yourself. But when you in JavaScript, it's all of these things that you have to write in C. They're all built into the language, but they still happen. They still happen. So even though this looks like just one operation, and you may think it's big O of 1, underneath the hood in JavaScript, in Swift, in C#, in Java, in every high-level language, inserting something to the beginning of an array is going to be a big O of n operation. So getting back to the beginning, why are we revisiting arrays? Because this stuff is important to know. Actually, if I were to, if you remember nothing from computer science, from all of this, you forget everything, algorithms, data structures, graphs, all of that. This is the one thing that I want you to remember. I want you to remember how arrays work. That should be the biggest takeaway, because no matter what, if you're front end, if you're back end, if you're anything, you're going to be using arrays, and you need to know how they work. And if you have a concept of how these arrays work, if you have a concept of memory, which now that you've started learning C, you will you start to see exactly what's going on with memory. Then you will understand how arrays work, and you'll understand how the performance implications work when you do different things with arrays. So that's why we're going over this stuff. What extra information and metadata is stored in a Python list? I don't know the exact stuff. You can look in the Python source code. It's all available online, but definitely things like the counts and the capacity are stored. There may be some more stuff, but I don't think there's too much more. I could be wrong though. I'm not 100% familiar with the underneath. Resizing or compromises space complexity. Yes, it does. We will look at that. I mean, it's still basically n. It's still basically n. It takes n space to store n elements, but then there's a little bit extra. But it's still big O of n. Is there a built-in counter for each time you add an element? Yes, there is, and a number calculates the number of extra spaces it adds. That's a formula. I think it's something like they multiply the space times like 1.2 or something, and then they'll round up. But I think that is implementation specific. So I think Python will be slightly different than Java or JavaScript or C# in how much they grow at the end. During an append, that's similar. Why wasn't Python designed so it reserves extra memory spaces in the back and the front? So the reason that it doesn't reserve spaces at the front is because, as you know, when you declare an array in C, you get a pointer that points to the front of the array. Why don't you reserve space at the front so something can grow at the beginning? I mean, I suppose you could. I think this is why people say that Python is not a very efficient language, same with JavaScript, is that if you're, for example, going to be adding to the front a lot, maybe you'll want to build your arrays like that, and which you can do in C, and which you cannot do in Python or in Java or JavaScript or Swift. So that's one reason to use C if you have very specific memory allocation requirements. Python adding to the ends. Why does it change? Okay, so again, this is because all of these are in a for loop. So for loop is n. So if you do something big O of 1 n times, that's big O of n. And if you do something n times, that's n squared. All right, what would happen if your memory is so fragmented and occupied that your OS cannot find another continuous memory block to allocate for an insertion operation? That is a great question, and the answer is a little bit complicated, but the short answer is that it'll start writing to your hard disk. Computers have they have different layers. So you have memory, you have caches, you have virtual memory, and you have your disk. So when your memory gets too full, it starts writing to your hard disk, which is very, very, very slow. Which is why when your computer runs out of memory, it starts running slow. Like it doesn't crash. It doesn't crash, but it's just slow because writing to the disk is, I mean, it's not a disk anymore, but in the old days, it used to be an actual spinning disk. writing to a physical disk is slower than writing to your memory. So that's why your computer will start to lag. Cool. All right. Great questions, everyone. I'm already liking this. I'm already liking this new format. All right. So it seems like people are in a pretty good mood. We got a few. Few people smashing their heads. No one's losing their lunch or breakfast yet, which is good. Okay, one person is losing their lunch / breakfast already. But all right, someone is indecisive about their sickness. But cool. It seems like we're overall in a pretty good mood, which is great. Because I'm super excited about this about teaching this unit for you all. This is when I first came to Lambda School. The theory of computation is honestly stuff that I didn't really know too well myself. So in order to teach it, this is one of the things that I had to study. And the more I studied it, the more interesting things that kept popping up. And as I started to learn about the history of computing and computation, it's really expanded my own knowledge. Like I knew a lot of the stuff already, but this really gave me a deeper understanding of what is code. Things like what is a computer, what is an algorithm, what is a data structure, how did these things come to be? What we're going to be going through all of that history, and I think that at the end of it, you will have a much deeper understanding and appreciation of sort of how this amazing thing called a computer came to be. On one hand, they're insanely complicated, and even if you spent the rest of your life trying to study how a computer works, you would never be able to learn all of it. But on the other hand, they're actually really simple. The structure of it is really basic and has been in place for hundreds of years, which I thought was really fascinating. You can break down a computer into these basic components, which are input and outputs, and then you have a CPU and memory. And those four components are the basis of computation. That computers today still follow that same model. So let's start looking at this theory of computation. If you watched the optional video for this weekend, you learned a little bit of history about people like Alan Turing, Charles Babbage, Ada Lovelace, Boole. What was Boole's name? Something Boole. I forgot his first name. George Boole. There we go. George Boole. And these are all really important people. Turing, in particular, is, I think, a favorite of computer scientists and programmers because Alan Turing came up with a lot of really cool stuff that programmers like to cite all the time. Among them is Turing complete. So Turing completeness is basically the bar that says if something is a real programming language or not. And he also created Turing machines, which were the foundation of that model that we talked about with computers. But before we get there, let's back way back and get into what is computation and what are computers. The movie also, is there an Alan Turing movie? That sounds familiar, but I haven't watched it. Oh, that one. Yeah, I haven't watched it. I need to watch it. I heard it was really good. Okay, I'll definitely put it on my to-do list. Before the end of this week, I'll try to grab a copy and watch it. Okay, well maybe you'll know a lot of the stuff that I'm going over, but I'm guessing that the movie isn't going to go into all of the nerdy details that we're going to cover here. So let's see. You're all in looking to get into the field of computer programming, software engineering. It's called computer science. So if you're going to be in this field, then it stands to reason that you should know what a computer is, right? Yeah. What is a computer? Well, the simple answer what is to that question is a computer is a thing that computes, right? It's something that runs computation. So what is computation? Um, a simple definition of computation is you take inputs, you run some operations on it, and you get some outputs. Um, those those operations that you run are called an algorithm. Algorithm is a set of steps, repeatable, predictable steps that take some inputs, processes them, and spits out an output. So that's what a computer is. A computer is a thing that runs algorithms. Now, there's a few keys. There's a few keys to this. One is that an algorithm is non-deterministic. So there's no randomness. If you give it the same inputs, you'll always get the same outputs. All right, that's important to remember. Now you can pass it a random input and get an output, but given the same inputs, you will always get the same outputs. It also needs to be able to be computed mechanically. And by mechanically, that's sort of getting at the no randomness. So these mechanical mechanisms, I suppose, have no randomness in them. They're repeatable and predictable, and given the same inputs, you always get the same outputs. So this is back in the 1800s. Even before then, when people were trying to figure out and philosophically, like, what does it mean to compute? What is computable? What can be computed? And people started coming up with these rules. Charles Babbage took this idea that it needs to be something that can be computed mechanically, and he ran with it. So back in the days, computers were just people. They were just human beings like you or me, who would sit down with pen and paper, or maybe a quill, I don't know what they used to write back then, and actually solve these calculations, which were needed for physics, for accounting, for things like that. And as is still true today, humans are very error prone. You can take the best human calculators, and they're still probably going to make mistakes. And they're also very, very, very slow. So that led to Charles Babbage creating the difference engine. Now, I don't know if you've seen, if any of you have seen this video, but I think it's pretty cool. There's actually on YouTube, you can see an example of Charles Babbage's difference engine in motion. So the way it worked is it had these things it had punch cards. And if you hear any old heads, old computer programmers talking about, back in my day, we didn't have JavaScript. I used to code in punch cards. Well, this was the original punch card machine. Basically, so how we always talk about binary, like you have either a 1 or a 0. Punch cards work the same way. A hole was a 0 and no hole was a 1. Or maybe it was the opposite. I'm actually not sure. But it would have these pegs, and it would detect if there was a hole or not, and that's how it would know what numbers were. And based on that, it would run these actual mechanical dials and do steps one at a time. So when you're adding is actually you would have to do it one number at a time. So each of these are like, if you have a 10-digit number, each of those would be one digit. And if you wanted to add two things together, it would do it sort of one place at a time. Yeah, I'm sure that drove people crazy. I'm sure hanging chads were a huge headache. Just like I'm sure that's like the equivalent of a semicolon, of a missing semicolon back in the day, or maybe single equal sign instead of double equal sign. But he created this mechanical engine so this is the difference engine. This was basically a calculator. This was able to do adding, subtracting, and things like that. You would pass in two numbers, it would add them up, and it would give you results. Based on these basic arithmetics, you could also do things, polynomial functions, which is like x squared, x cubed, things like that. And based on that, they were able to approximate a lot of different things like square roots, which square roots are very, very, very difficult to calculate by hand. But you're able to approximate them using these mechanical objects. So he created this giant calculator. It was the first of its kind. It cost a ton of money, but it was a way of doing calculations in an error-free way. And by error-free, I'm guessing there were still errors. Maybe hanging chads and such. Of course, you could maybe you punched the wrong hole and you put in the wrong input, so it's not error-free, I'm sure. But just like code is not error-free, right? Like there's always going to be some human error. But this was the first step into creating what is known now as computers. After the difference engine, he was working on he started working on the phase 2, which was the analytical engine. Now, where is that? I guess it's not in here. So the analytical engine was taking this calculator and adding some more functions to it. Things like for loops and conditional branching. Now these conditional branching are things like if this, then do this, else do this, which you all should be very, very familiar with. For loops, looping is again something you should be very familiar with, which aren't present on a regular calculator. And then they also have memory in the form of cards. Now this would be this never got completed because as you can see, these are pretty huge undertakings even back then, back in the 1800s, and this was an era where manufacturing was really kicking into swing. The Industrial Revolution was happening in America. Babbage, I believe, was in the UK. I think, but they were trying to solve this problem of how to do calculations more accurately and quickly, and eventually he wanted to move on to create this more powerful thing called the analytical engine. That unfortunately never got finished due to problems with funding, problems with his boss, things that still come up today. But he worked with Ada Lovelace. Ada Lovelace is known as the first computer programmer who used, I think, the difference engine to calculate Bernoulli numbers. And she's the first person to use the punch cards to, quote, program this computer. Now, let's skip ahead a little bit and get to Turing. So, the Church-Turing thesis. Yeah, so what Turing was thinking about was, not just Turing, a lot of people were thinking about this. Like, what can be calculated? We talked about what computation is. Well, what does it mean to be computable? And maybe more interestingly, what is not computable? So the basic idea starts from a Turing machine. So a Turing machine is it's a mechanical machine, very similar to what Babbage built, that can do certain operations, certain arithmetic operations, and it has a concept of infinite tape. So the infinite tape is really important too. We're going to get back to that. But basically, the tape is that it can write something on this tape or rewrite it, and it can move along the tape and set different values, and then it can read those values back. It also has things like conditional branching, like if it has loops, you need to be able to store variables on the tape. And anything calculable, anything computable, the definition of that is something that can be computed by a Turing machine, by this arithmetic unit and this infinite string of tape. So that should sound familiar as I described earlier, right? Like what is a computer but a CPU, memory, input, and output? Now we have some pretty complex inputs, right? Like we have keyboards and mice. Outputs, we have monitors, we have sounds, we have We have the internet. The internet is sort of input and output. We have all these different sensors, like maybe temperature sensors or audio, things that read and write audio. So inputs are very complicated. Our chips, our CPU chips, are insanely complicated now with billions and billions of transistors. And memory, memory, instead of an infinite string of tape, we have gigabytes of bits, right? So a bit is either a 1 or 0, and that's a byte is 8 bits. A kilobyte is 1,000 bytes, or 8,000 bits. Megabyte is 1,000,000, and gigabyte is 1,000,000,000. So it's not quite infinite, but when you have billions of bits, it's roughly equivalent to, for practical means and purposes, it's equivalent to an infinite piece of tape. So what is depressing? A function on the natural numbers is computable by a human being following an algorithm, ignoring resource limitations if and only if it is computable by a Turing machine. Seems that AI is overtaking mankind by natural selection. Yes, which is why, so I don't know if this will ease your depression, but as I said, a lot of things can be calculated, but maybe more interesting, what cannot be calculated. So that, let's see, where's the halting? So there became a whole discussion about what cannot be solved. The most famous of which, and maybe most useful to computer scientists, is the halting problem. So computers can't solve everything. Computers cannot determine everything. For example, a computer cannot look at a piece of code and determine if it's going to loop infinitely or not. Why is that? You can look into it, but basically, it's possible to present a case where this doesn't work. Are there any philosophy majors out there? I think this should be very familiar to you. A lot of the stuff we're going to be going over is very philosophical. So there's no way for a computer to tell if it's going to infinite loop. Which is why when you put in code, if you get an infinite loop, it'll just keep going forever. Sometimes you may get a stack overflow. Stack overflow is if you have infinite recursion, which is recursion that never returns. So like let's say if you have recursion that says like if you're trying to do factorials, but instead of doing -1 each time you did +1, so the number kept getting bigger. That would go on forever, and your computer would have no way of telling when it stops. So if it could get a stack overflow, which is basically you run out of memory, and there's a difference between running out of memory and going on forever. But for practical means and purposes, that should work. But this is also a limitation of AI. Like there's a lot of things that AI just simply cannot determine. One way that we are getting around this in more modern times is that even though computers cannot determine a certain thing, they can get really, really, really close. So like going back to the halting problem, like maybe a computer can't tell if something goes on forever, but maybe after like 1 billion cycles, it'll say like, I'm 99% sure this is going to infinite loop, and it'll return. That's similar to things like machine learning, where you can say like, I'm 99% sure this is a picture of a cat, but I can't, I can't be 100% sure. Like, I don't think there's a way a computer can be 100% sure that something is a cat, but we're getting really, really, really close. So it's the joke about like computer scientists, right, or mathematicians, where you may think it'll never get there, but you can get close enough. You can get close enough, which is where a lot of things like machine learning are going now. Is it gigabytes? 1 billion? Marshall, homework for today is over 2 days. The arrays assignment is over 2 days, and then for the next 2 days, you're going to be doing hash tables. Is it gigabytes 1 billion bits or 1 billion bytes? It's 1 billion bytes, but it's actually a little bit more than 1 billion. So it's actually 10 to the 3rd power. Now, we usually say 1 billion. I'm going to use Python. Apologies for jumping back and forth with Python, but Python is really easy to demonstrate these things. So when we say like a kilobyte, we say it's 1,000 bytes, but actually it's 2 to the 10th, which is 1,024. So it's pretty close to 1,000 bytes, but not actually. If you say 2 to the 20th, this is a megabytes. It's actually not a million, but it's 1,048,576. So a gigabyte is actually 1,073,741,824. But it's pretty close. It's pretty close. So we actually say it's a billion. This is actually funnily enough, oddly enough, when you buy a hard drive and it says you're getting 1,000 like a gigabytes of disk space. A lot of times they're actually saying you have a billion bytes, which is slightly less than an actual gigabyte. So that's a marketing way of screwing you out of a few extra megabytes. But that's something you have to be careful with. But for most means and purposes, we just consider it a billion. Yeah, so Carlos, I think this is interesting because a human can look at something and tell if it loops infinitely, but computers can't. Let's see, humans operations are only run by one CPU. If you have another CPU that examines, I think if you have another CPU that examines the loop structure, I mean, it should theoretically determine that it would be undecidable, right? Theoretically, but what this halting theorem, the halting problem says is that you can give it maybe like the case we said where the recursion is increasing. Maybe you can write a program that detects that will loop infinitely, but you can pass it a function that will make its brain explode. So the halting problem, this is very, very, very philosophical. Where's the proof? I think it's Gödel's incomplete. Gödel. I think I'm okay, I lost it. Gödel. Well, anyway, the basic proof is that you say if you have a function f, and that function f is a function that will determine if something loops infinitely. You pass in another function, and then you say if function is true, then run an infinite loop. So basically, if that function does not loop infinitely, then run an infinite loop. So basically, what that's saying is that if it doesn't loop, then you loop infinitely, and if it does loop, then you don't. It's a little bit weird, and it's hard to explain. And if I'm being 100% honest, my understanding of it is not too clear. But basically, it's impossible to create a computer or a function where you can't where you pass this function and it doesn't make its computer brain explode. So yeah, so if Terminators start coming, maybe this might be the most useful thing you ever learn. Just start feeding these our robot overlords these infinite looping functions, and we should be able to save humanity. How do you pronounce those two dots? I never really. Gödel. I'm not sure. Are you going to learn binary? Yes, you are going to learn binary. You're going to be going over more of it next week when you get into computer architecture. We're gonna run through it in this unit, but we're gonna look at it more through the lens of logic, and that'll be for I think tomorrow or maybe 2 days from now. But we're gonna be looking at more in terms of logic here instead of things like counting and binary, which you'll go over more next week. You've read that the 1023rd byte is 10 bits instead of 8 bits. Have you come across this? I haven't read that. I don't know why that would be. That just seems odd to me. Um, why would you have 10 bits instead of 8 bits for the second to last byte? Yeah, Wanjay, I haven't come across that, but I would be curious if you find where you read that. I would be interested to see what the reasoning is there. Okay, yeah. I I respectfully ask your forgiveness for any of my mispronunciations. I'm sure I'm mispronouncing a lot of things. Uh, for example, automata or automata. I don't know how to say that at all. Um, automata theory. So getting back to Turing, the halting problem. We have Turing machines. The Church Turing thesis is saying that anything, the definition of computation of something that's computable is something that can be computed using a Turing machine. And Turing machines have become the foundation for what our computers are today. Um, Again, a Turing machine. Let's click into that. Turing machine. So a Turing machine is a computation. You have a thing that can do various mechanical computations and a long string of infinite tape. You pass it in inputs. It does these calculations. It uses these sort of as scratch base to write down intermediate calculations and values, and it spits out an output. So anything that can be computed, anything at all, can be done by this theoretical Turing machine. Again, the processes that are done with the mechanical part, that's an algorithm. So if anyone asks what is an algorithm, you know what to say. It's something that takes inputs, it does the thing, and then it spits an output. Now, when we teach algorithms, so back in week 2 of computer science, we taught algorithms. A lot of what we taught were pretty complicated algorithms, right? Like these are tricky things that are meant to stretch and boggle your brain. So those are definitely algorithms, but those aren't all that are algorithms. Like algorithms can be really simple also. Algorithms can be something like take a list of names and capitalize every third name, right? That's a very simple algorithm. Or it can be read this CSV file, average out all of the numbers in column number 3, and then spit out the return value. So that's an algorithm too. So algorithms are basically anything that takes an input, runs some operations, and then spits out an output. Data structures. Data structures were from the second half of week 2. Data structures are related to this spot on the memory, on this memory tape. So data, this memory holds data, and in memory, data is everything is either a 1 or a 0, right? 1 0 1 1 0 0 1 0 1 0. What does that mean? It doesn't mean a whole lot unless you give it some structure. So the first thing to do is to group them into what we call bytes. So bytes are nice because in 8 bytes you can store 256 values. So that's again 2 to the 8th is 256. ASCII characters. If you look at ASCII tables. So using a character, when you look at the car like in CHAR, that's a 1 byte data type that stores each of these. So this goes up to 127, but these are all of the different characters you can use. There's Unicode. So Unicode is expands this into much larger things, which includes things like Chinese characters or special characters or things like that. These weird characters I think are also included, that like this OE thing. Marshall, the answer is yes, but not. So that's more. We'll talk more about that in a couple of days. But what that means is yes. So if you have a 32 bits, you can only access 4 billion, right? So we decided 2 times 32 is about 4 billion. 4,294,000,000, blah blah blah, right? So if you use this, then you can only access numbers between 0 and 4 billion. Now, if you have 4 gigabytes of RAM, right? If you have 4 gigabytes of RAM, then you can access every individual spot using only 32 bits. But if you have more than 4 gigabytes of RAM, which your computer probably does, it probably has closer to 8. Let me see what my computer has. Overview. So I have 8 gigabytes of RAM. So I would not be able to access if I were to just use 32 bits, I would not be able to access all of my RAM. So you need to do 64 for things like this. Actually, I mean, with 8 gigs, you only need 33. But we usually just, in computer science, everything is powers of 2. So we just go to 64. It's not quite that simple. Like the Nintendo 64 did not have 8 gigs of RAM. But that's sort of what it's getting at. If you have 32 bits, you can only go from 0 to 4 billion, which you do start hitting that limit when you get to when you're starting to get to things like 64 bits. Nintendo 64 is tricky because I actually think they just had 2 32-bit processors, which was a little misleading. But again, this is just marketing speak. At that time in the 90s, everyone was just, the more bits, the better, without really knowing what was going on there. But great question. Okay, so a data structure is we have this infinite tape. It's structuring this. It's again structuring this data. A data structure is structured data. That's a little bit self-referential and obvious, but it is a way of organizing these things. Like a car is a byte, is 8 bits, and then you have things like an integer. An integer will be 32 bits or 4 bytes, and that lets you put a number between 0 and 4 billion. Or if you add any negatives, it's between negative 2 billion and positive 2 billion. You can also do things called floats, which floats are basically like scientific notation. You have some bits for the number, you have some bits for the power, and some bits for what the back exponent is. Floating points are really interesting, and I wish that we had time in our curriculum to go over floating point numbers. But that's something really interesting that you can look up. How do you fit? How does floating point fit into 32 bits? Let's see. Yeah, it does go up each time, and that's why old NES was 8 bits, and then you get to 16 bits with things like Super Nintendo and Genesis, and then 32 bits with PlayStation, 64 with N64. Let's see. So a data structure is a way of structuring this data. Now you've seen some of this with structs. So structs were one of the first ways of determining that. Like structs are a way of structuring, are saying like these bytes represent this, and this is how it's divided up. Let's see. Cameron put a good question up here about the person structs. Where is it? Maybe it didn't help. So this is a person struct, and this is I guess you can call it a data structure, but it's saying that these 20 bytes are, the first 4 are going to be a character pointer. So that's 8. That's 8. It's 8 on my machine. It may be 4 on other machines. But I'm using a 64-bit processor, and then ints are 4, 4, 4. So this is going to be 20 bytes of structured data. You learned about things like a queue, right? Like a queue and a linked list, and it's like a linked list is saying that, all right, you have the cell, the first half is going to be your value, and the second half is going to be a pointer to the next value in your list, and it's gonna, and these, you know, these pairs can be all over the place. So that's how that's structured. But basically, it's just saying it's a way of organizing these ones and zeros on this long piece of infinite tape. That's what a data structure is. That's what a data structure is. Key difference is an integer is not a data structure, it's a data type. I mean, I suppose you could think of it as a data structure, but strictly speaking, that's a data type, whereas something like an array or a linked list or a queue or a binary search tree, those are data structures. But I think that's more of a practical definition than a strict definition. And when we if we start to think about memory as a string of infinite tape, then that brings us to what is the simplest way of structuring this data, of not just structuring one type, but structuring multiple data points, storing multiple data objects. That's the wrong word. What's the word I'm looking for? I guess storing multiple data types. That would be a data structure. So the simplest one would be an array, right? That's you have your data, and then the next one is right next to it, and then this one is right next to it, and this is right next to it, and it's all contiguous on this piece of tape. And if you know that, if you have it all right next to each other, it's very easy to jump to the different locations, right? So if you know where the start of your array is, and you want to get to the fourth item, then all you need to do is if you know how wide your item is. So if you have a car, it's going to be 8 bits. So when you start at the beginning, and if you want to get to the second one, you multiply by, you take the starting address, add 8 to it, and then you're at your second item. If you want to get to the 10th item, you take 8s and you multiply by 10, and you get to the 80th item, and then that's your 10th item. Now, there was a question up here about why does it have to be continuous, and that's why it has to be continuous. It's because this calculation is super fast, right? Like multiplication is really easy. You can do it. You can crank the thing, and it'll rotate the dials, and you can figure out the multiplication and the addition pretty quickly in just a couple of cycles. However, let's say you wanted to get to the 10th item and you only have 5 here and then a pointer to the next 5, you can't do that calculation. You would have to go to the 5 and then get to the pointer and then jump to the new memory address and then do the next 5 and then find that there. It's not quick. That would not be quick. And then that would turn it into a big O of n operation instead of a constant time operation. That's why if you want to find the nth element in a linked list, it's big O of n. Whereas if you want to find the nth element in an array, it's big O of 1. Also, linked lists take up twice as much space as a regular list because, again, half is for data and then half is for pointers. So using a linked list would take up twice as much memory. The nice thing is that you can, if your memory is fragmented, it's pretty easy to fill in all of these little fragment holes. Also, as we saw from the example, it's really difficult to add stuff to the beginning of an array, but linked lists are easy to just put a new thing at the beginning. So there's some trade-offs. But for most means and purposes, arrays are going to be what you use for the fact that you get big O of 1 efficiency to access, to read, and to write. And that's going to bring us to the homework for today, which is you're going to start implementing your arrays in C. How come sets look things up in O of n? Sets, are you talking about like Python sets, like s equals set, like this? Yes. That is because sets are underneath the hood. Sets are using hash tables. So we're going to be getting to that in the second half of the week. So I'm glad. These are great questions. I'm loving this. I'm loving this. Sets are using hash tables underneath the hood, and hash tables have lookup in big O of 1. But they also come with some pretty serious costs of their own, which we'll be looking at in the second half of the week. Yes, you would have to know the key name for big O of 1. So that's sort of the difference between arrays and hash tables. Or hash tables you may know better as dictionaries in Python, or objects in JavaScript. I don't know what they're called in Swift, but it's probably something similar. Associative arrays or hash maps or things like that. They're all referring to basically the same thing, which is hash tables under the hood. And hash tables are just arrays under the hood, but with a little bit of magic done to get the indexes. But we'll be going over that next week. Not next week. We'll be going over that in 2 days. So it could be big O of search if you don't know the key name, right? Yeah. So if you're looking for an item in your dictionary, in your array, yeah, that would be big O of n, because you would just have to check each item to know if it's in there. If your list, you could get some optimizations, like if your list is sorted, or if it's in something like a binary search tree, you can get optimizations, or a heap. But that's stuff that you can. So once we finish this, you should be able to connect the dots from the stuff that you learned in week 2 with data structures and algorithms, and these things should start making a lot more sense. Like already, linked lists should make more sense to you now that you know what pointers are, right? So you don't need to know the order. Normally, a set is better than an array. That's a not necessarily. Not necessarily. Sets have a lot of wasted space, whereas arrays are very tightly packed. So arrays are basically the most efficient you can store data, since everything is packed side by side. That's like the theoretical. Like, how do you store 10 bytes most efficiently? It's to have them right next to each other. Sets use up a lot of wasted space. Same with dictionaries and hash tables. But that'll make more sense when we get to that. I love these questions though. All right. Why don't we take a break, and then we'll jump in. We'll start looking at C. We'll get into this assignment. We'll talk through what you're going to be doing to create your arrays, and hopefully you'll start to see. You'll start to connect the dots between allocating memory, running operations, doing algorithms, doing accessing memory, and things like that. This should start to paint a much more comprehensive picture of what's going on underneath the hood of all these programming languages. So let's take 5 minutes, and we'll jump into C and arrays. Yes, I love it. I love it. All right, we are back. Am I muted? I don't think so. Okay. All right, so we're back. There's a lot of these questions here. These are all great questions, by the way. A lot of these questions you will you'll be figuring out the answers for yourself. Like which array methods are big O of n? Is it just the add delete methods? We'll see. We'll see. You'll be implementing all of these, or at least the basic ones. There's some more as stretch goals, but these are the main ones. And the answer to which ones are big O of n is it depends. It depends. But you should be able to look at your C code and figure it out. There's which one was I looking at? Here we go. How do Python array methods, deletion, insertion, etc., under the hood compared to C array methods? The answer to this one is that they're exactly the same because Python is written in C. So you can actually look at the C source code. So C Python source code. It's on GitHub. It's all Python is completely open source, and it's all written in C. So, you know, if you're stuck on your homework and you want to be clever about it, you could just go and all of the answers are in here. You can see how Python implements all of these methods in this repo. I will say that this stuff is pretty complicated, and it's not so straightforward to look through to read through it. But remember, under the hood, C is just running. Python is implemented in C, and the same thing with things like JavaScript. These are high-level languages that implements low-level language things like C, and then C gets compiled into machine code. And then machine code gets compiled or gets run by the computer. Machine code is a set of like instructions that these chips can understand. So it'll take something like a very basic like multiplication, and it'll break it down into machine instructions. So there's this whole hierarchy that we're going to go more into later. But just remember that underneath the hood, high-level languages are built in low-level languages. So when you're doing insertion, in C, remember you're actually just implementing arrays in Python, or if you so please, in JavaScript or Swift, whatever your primary language is. So when you're creating when you're creating an array and you're inserting something at the beginning of it, remember that's a O of n operation, no matter what language you're running in. And this is because we're all working with the same model here, right? They're all running on the same computer. They all have the same processor, and you have the same strip of memory. And theoretically speaking, this is what an array is. An array is a contiguous block of memory, right? Each slot is a single type, and you can access them in constant time by multiplying by the index. Any language, high level, low level, anything. Certain operations are very expensive, like this. Remember, strings are also arrays. So it's just an array of characters. So when you're, for example, adding two strings together, right? Like if we're doing like A equals ABC, B equals 1, 2, 3, and if we do A plus B, what this is doing is actually, you have this small array and you have another small array, and what it's creating a new array of characters and just copying over the items one by one, and then just copying over the second string one by one. So we have this length 3 string. This is creating a new one, length 6, and it copies things over one at a time. When you do something like a for loop, like let's see, what's for I in range? I know I'm writing Python in my C, which is really confusing, but I apologize. Let's see, string equals empty string, string plus equals fi. So let's say we run this code. It's basically just 100 times we're adding a number to the string, right? Every single time it adds something. It can't just keep growing the string. Every single time it does this, it's creating a new one. So since we're running this 100 times, you're creating 100 new strings, and everything else is getting thrown in the garbage. Now languages like Python have a garbage collection, so that stuff gets cleaned up automatically. But in C, there's no garbage collection, so you need to actually call free on these. A garbage collection is something that does free all at once instead of doing it each time. But something like this is really, 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 really inefficient. So you should never append to a string in a for loop, in any language, in JavaScript, in Swift, in anything. And if you understand how arrays work, you might understand why this is a terrible thing to do. That makes sense? Does everyone? This is a really important takeaway. Okay, so I want to make sure everyone understands this. This assignment you're doing here, this is not a C assignment. This is not like I'm going to be a C programmer, so I need to learn to do an array in C. I'm going to be a JavaScript programmer, so I need to understand how arrays work in JavaScript. I'm going to be a Swift programmer, so I need to understand how arrays work in Swift. This is how strings work in Swift. This is how strings work in JavaScript. All right, so that's why we're doing this. Not because you're going to be a C developer. It's because because every high level language does this. All right, that makes sense. Okay, I'm gonna assume that makes sense, and please stop me if anyone has any other questions. All right, but if not, let's take a look at this. Where are we? All right, sweet. Okay, so we have some intro here. You'll be implementing Let me okay. So for the homework, as a brief intro, you're going to be implementing for day 1. Create, destroy, resize. You can skip for now. Create, destroy, read, and append. I think, yeah, do append before read. Otherwise, you'll have nothing to read. So create and destroy are pretty easy. Basically, you're doing mallocs and setting your initial values. So these should only be a few lines of code. Read is also pretty easy. Your actual array, the actual array is going to be stored in this pointer to character elements. These double stars may be a little bit confusing, but remember a char star Char star, you can think of it like a string. So this is basically an array of strings. Again, it's a little bit tricky because it's actually a pointer to the beginning, a list of pointers, and then each of those pointers points to an array of characters. But I think this will make sense, a little more sense once we start getting into it. Okay, the one that's going to probably take the most time is going to be insert. And this, so you don't have to do resizing yet, but basically you're going to need to declare your array of elements, and then inserts, be able to append to the end of that until your list is full. And that'll be it for today. And then tomorrow you'll be doing insert, which allows you to insert at an arbitrary location, remove, which lets you take an item out, and then you need to shift everything over. Insert will also make you shift, and then resize. If you go over your initial capacity, it should double the array in size. All right. Let me go through answer some of these questions, and because I think there's a lot of really good stuff here. Is there a built-in counter for each node for each time you add an element? Yes. So that counter you can see is going to be right here. So we literally have a counter here that will increment and decrement every time you add or remove an element from your array. This is how Python does it as well, and you're gonna see where it comes into play as you're implementing this. How does Python specify how much extra memory? So here, for this assignment, I'm just saying to double it. But the way Python does it is, the way Python comes up with this number is it's just a little bit bigger every time, so as I mentioned in the video, when you add something to the end, if there's room, it's a big O of 1, right? But if you're out of room, then you need to create this new array and then copy everything over, and that's going to be big O of n. So we still say append is big O of 1, even though it's only sometimes big O of 1, and then occasionally is going to be big O of n. But the way they determine the number, how big the space gets at the end, is that they just made it get bigger every time. So on average, it's still just big O of n, big O of 1, excuse me, which is a little confusing. But just know that the more you call it, the less often you'll have to call this this resizing function. But they also don't want to waste too much space. So it's all a balance. This works for most means and purposes, but again, if you have really strict memory, like if you're doing something on embedded hardware, you may want to write it in C in order to get like the most optimal memory allocation algorithms for your particular application. During an appends, we just talked about this. Yeah, we also talked about why you didn't have something in the back and the front. This could be an exercise for you to do if you want to implement for yourself. You could try making extra space at the front, but I mean, I think you end up running into the same problems because you'll just have to resize the other way. And how much space do you put at the front? And you're going to end up wasting a lot more space in general. This is a point that I saw a lot of people ask, so I'm gonna go over it one more time because this is a very important key. So this adding to the back is big O of n, right? Adding to the back is big O of n because we have a for loop, and I know that you learned, right? When you have a for loop, that tells you that it's big O of n, right? We have 0 to n, so we do something n times. Inside of here, we have a constant. So this is going to be big O of 1. So this is big O of 1. Sorry, big O of 1. This inserting to the front is big O of n. And that's because we have 10 things in our array, and we want to stick something in the front. first we have to move the last one over one, and then the second to last over one, third to last, this one, this one, this one, this one, this one, until we have space at the front, and then we can put our new element there. So this is that's an n operation where n equals the length of this array. So when you have an n inside of an n, that's a for loop inside of a for loop, and that gives us n squared. Right? So the important thing to remember here is just because you don't actually see a for loop, you might have a hidden for loop, right? So inserting something at the beginning, that's a hidden for loop that you need to be aware of. And now that's why you have a for loop and a for loop, and that gives you n squared. Are these add methods adding an index or adding a value? Which ones are you talking about? Are you talking about append and inserts, or are you talking about the homework, the C homework? The answer to both is whatever is you're doing it like Python does. So this is just Python. So you can run this code in your Python interpreter. So if we do x equals 1, 2, 3, and then we do x dot append 4, and we have x equals 1, 2, 3, 4. And if we do x dot inserts 0, let's do 10, this will insert 10 to the beginning of our list. So append adds something to the end, and insert will insert something at an index. Now, you're not always inserting something at 0, right? What if you want to insert something in the middle? What's the big O of that? So let's say you want to do x.inserts. So our thing is length 5, so let's insert something at index 2. 1, 2, 3. We put something sort of in the middle. What's the big O of that? Well, if you look at, let's see, Python time complexity, you will see, so append is big O of 1, like expected. Insert is big O of n, but wait, there's something else that I was, extend. Okay, I thought it would say k, but anyway, basically the big O is whatever the, like if you're inserting something second to last, like if, then you only need to scoot over one thing. But if you're inserting if you're inserting something in the middle, that's going to be big O of n over 2. But since we ignore the coefficients, we just call that big O of n. What about adding an element to the beginning or end of an array in C? So when you do that in C, you're going to need to do the same, exactly what we described, and that's what you're going to be doing for your homework. So you won't have to do that for append. For append, you're just sticking something at the end. But when you do insert here, you're going to need to scoot everything over before you insert your item. All right. So to answer Adrian's question, again, this big O of n operation that we described, you will need to implement that for array insert. All right, you're going to need to say, all right, I'm inserting something at index 4. So everything above 4, you're going to need to scoot over to the end. And there's some, you'll need to move over 5, 6, 7, 8, 9, and so on until at the end of the array. You're going to need to move over one space. Now, you're going to want to start from the end to prevent overwriting your old values, but you're going to, so like if your thing is 20 long, you need to move 20 to 21, 19 to 20, 18 to 19, 17 to 18, and so on until you get to, what did I say, 5, and then you're 5 to 6, and now 5 is empty, and now you can put your new element right there. Would it still be O of n because you're still copying part of the array? Yeah, so if you're inserting something in the middle, it would be n over 2, but we just call that O of n. So you're going to need to scoot over everything. I like to think of this as a bookshelf. Like, what do you do if you want to insert a book in the middle? Like, you would need to slide over all the books over here, and then put your book there, right? there's no slide over function in C or in any programming language, so you'll need to move the books one at a time. All right. What happens to previously allocated memory when you delete an element from an array? When you delete an element from an array, you will need to, if it's a value in the array, you just need to override it. So if you just have an array of ints and you want to change a 5 to a 6, you just change the 5 to a 6 and you don't have to do anything. But if you have a pointer to a string and you want to delete that string, you're going to need to free that pointer as well. You know that because in order to create that string, you need to malloc it. And anytime you call malloc, you need to call free. I'm going to repeat that. I'm going to repeat that many, many, many times. Anytime you call malloc, you're going to need to call free, like literally every single time. So when you do create, you're going to need to do a few mallocs. Like you're going to need to malloc room for this elements. Every time you create a string, you're going to do a malloc there. And every time you delete them, you're going to need to free it as well. There's some hidden mallocs as well. Like if you do calloc, which I recommend for allocating your elements. Use calloc. Calloc isn't malloc, but it is malloc under the hood. If you use like string dupe also has a malloc underneath the hood. Since you're mallocing, you're duplicating a string, but you're mallocing this extra space there. So this is also malloc. So anytime you call string dupe, you need to call free. Anytime you call calloc, you need to call free, and so on and so forth. So anytime you allocate memory, you also need to free it in C. Otherwise, you get what's called a memory leak. How bad is a memory leak in C? How bad is it? Depends. If you just have a constant memory leak, it's not terrible. Like if you're just declaring something once and you forget to free it, no big deal. But where it comes into problems is when your program is running, where it's running and every cycle it adds a little bit of memory that's not freed. So that can be something like I don't know. You see this a lot. Like you'll see as you run your program, slowly your computer will just start to run out of memory, and then you need to reset the program. You see that in like actual like delivered code very often, where some coder left some bug in and there's a memory leak, and you need to restart the program every now and then because it just takes up all your computer's memory. So that's the real danger. That's the real danger if there's a hidden memory leak. Sometimes you can have processes running like in the background on your computer that just keep going on forever, and the memory will just grow and grow and grow. So it can be really bad. It can be really bad if it causes your computer to run out of memory, because as we mentioned before, when your computer runs out of memory, then it has to start writing and reading from disk, which is super, super, super slow. Yes, Adrian. Yes, this all assumes there's enough free space at the end of the memory block when you're doing your insert. If there's not enough space at the end of the memory block, then you need to resize you need to allocate some more memory, copy everything over, and then you can do your stuff. So you can copy everything over and then do the insert, but it's probably faster and faster in terms of processing power to do the insert smartly. So resize your array, copy the first half, drop your element in, and then do the back half of the array, rather than copying the array and then doing the insert and scooting everything over. Does that make sense? But if you want to resize by just copying, run the resize function and then do the insert after that, I think that's fine for this assignment. Is virtual memory when it hits? So virtual memory is just this idea of, so when we talk about Turing tape and the infinite memory, as far as your computer knows, you have infinite memory. So what it's going to say is you're going to say malloc, hey, I want to malloc this much memory, right? And then the computer will give you back a memory block. Now you don't know where it's stored. You don't know where it's stored. You don't know if it's on if it's in your memory, if it's in your on your disk, if it's in your cache. If that's sort of what virtual memory is. It's you just treat it as infinite memory, and you have these sort of black box operations, which is reading and writing from memory. And maybe it's slow, maybe it's fast. You don't know. Your program doesn't know. That's all happened by the computer. For this one, I recommend looking into the source code. It's pretty interesting. And sometimes you can discover some neat stuff about how things work. But again, warning: this is it's pretty obtuse, I would say, and it may be. But you can find stuff like the counters, like the counts, and see what Python does with it. Fragmentation and defragmentation. So usually when we talk about fragmentation, we talk about your hard drive, because hard memory. So memory is that's like cleared out every time you turn on and you turn off and turn on your computer. Like memory, RAM. When we talk about memory, we talk about RAM. That's cleared out, and every time you turn off your computer. So that doesn't get fragmented that often. Also, each program, like when you load up a program, like right now I have Slack running, I have Firefox running, I have Sublime Text running. Each of these have their own reserved block of memory. And that's usually its own block. That should be a contiguous block as well. If you go out of that, bad stuff starts to happen. But what happens on your disk, on your hard disk, is fragmentation, because that stuff will stay there. So then if you create a lot of small files, like if you create 1 million tiny text files and then you delete half of them and you delete every other file, you don't get half of your memory back, right? You get these tiny little blocks that are not useful for anything. And then you start, if you run out of space, you may have like 10 gigabytes stored free on your disk, your hard drive, but if they're all in little blocks, then it's not very useful. Then you have to do, your computer does what someone mentioned earlier, where you have your contiguous block and then a pointer to the next block, and then a pointer to the next block. Your computer starts to do that, which, as you can imagine, is really, really, really slow. So that's why your computer will run. You want to run defragmentation every once in a while, or if you never delete stuff, then you won't get any fragmentation on your disk. So that's another way to do it. Yeah. Windows is you want to defragment pretty regularly, and also you want to defragment before your computer gets too full, because you need to have that swap space, right? Like you need to if you want to defragment something, you need to put something in the blank space and then reshuffle the stuff around, and then you can put it back. So if you don't have that space, then it needs to split it up and put it here while it defragments here. Then you need to put it back, and then that's why defragmentation can take a billion years sometimes when your computer's really full. Defragmenting SSD is wasting time. I don't know the answer to that. I don't know the details enough about how solid state drives work, but I do know that I haven't had to defragment my computer in a long time. I don't remember the last time I've defragmented anything. Also, for me, my hard drives are so big that I rarely run out of space anymore, unless I have like giant blocks of media, which I tend not to delete. So I don't know. Why does Linux not need a disk defrag? I don't know the answer to that either. I think fragmentation will still happen on the disk. Maybe it just doesn't have a disk defragmenter. Does it have an automatic disk defragmenter? I'm not sure. Does Mac have a defragger? These are questions that I don't know the answer to. Okay, interesting. That is interesting. There's also different ways there's different file systems. There's different ways, there's different formats. You can think of that as a data structure also. Like FAT32 is like a way of storing data and organizing your data. So different operating systems have different storage types too. So that may have something to do with it. Which array methods are O of n? You will figure that out with your homework. Resizing an array compromises space complexity. Again, what it really does is okay. So one important thing. So one, you have some extra space at the end of your array. So that's a little bit of wasted space. But also you need to have double. You need to have at least twice as much space in order to run the resizing array method at all, right? Like say you have a humongous array with 3 billion characters, right? 3 billion characters, that's going to take 3 gigabytes to hold. Let's say you only have 4 gigabytes of memory. That's going to be impossible to resize because you'll not only, if you're going to resize it, you're not only going to need to have enough space for 3 plus some extra, you're going to need 3 billion and then 3 more billion and some extra at the end, and then you have to copy stuff over. So so that does add to the space requirements. You need to have enough at least to run this doubling up. You may have heard this in terms of sorting. So for sorts, I don't know how much sorting you did. I think we recently, I don't know if I think you did quick sort maybe for some of your coding challenges. But anyway, there's a concept of in-place sorts, which means that it all happens in place, so you don't need any extra memory. And then you have something like insertion sorts, where like you have 2 copies and then you move things from one copy to the other. So resizing is not an in-place operation. Inserting n squared. Again, I'll reiterate this one more time. Inserting to the beginning is big O of n, but when you're inserting something to the beginning n times, then that becomes n squared. Is there a difference between how a contiguous block of memory is allocated when inserting versus appending? No. So there's no difference between how the memory is allocated. All you do, which you'll see in C, is you say, how much do I want to malloc, right? Like you say, I want 20 bytes of memory. You say malloc 20, and then it gives you back these 20 bytes. The counts is doesn't matter if you're adding to the beginning or the end. You just need 20 bytes to store all of your elements. So allocating itself will happen exactly the same, and it'll return a pointer to the start of your array. Yes, block of memory does have to be continuous. Great question. Adding elements is the ends. Okay, here's a good question. Here's a question for the class. Adding an element to the end of the array is, so this is actually a big O of 1 operation. So this is constant, adding to the end of an array. What about adding an element to the end of a singly linked list? Here's a question for the class. What is the big O? What is the time complexity to add an element to the end of a singly linked list? We have O of n. We have O of 1. Any other guesses? I see Jonathan typing. Those of you, Tsai, why is it O of n? And Brian, why is it O of 1? The answer is that you both might be right, but it depends if you can justify it correctly. That's the thing with these big O's. There's no absolute answer. It's you have to say it and then give why you're counting it, because both of these could be correct. While they're typing, is there a singly linked list data structure in Python? I don't think there's not by default, but you can implement one pretty easily. And I think you did implement this in week 2, didn't you? Pretty sure you implemented linked lists as part of your data structures assignment. How does it compare to the implementation in C? Since Python is written in C, they're going to be pretty much the same. but Python in general adds a few extra things to all of your data structures. So C will be a little bit more efficient. Okay, Brian, you can get the number of nodes, then add one more node to it. You have to traverse the entire linked list to get to the end of the list, change the pointer to the last element to get to the new elements. And Adrian, does big O depend whether you keep a reference to the tail of the list? Yes. So Adrian, you hit the nail on the head. Sai, you're correct that if you don't keep a reference to the end of the list, then you need to then you do need to traverse through the entire list to get to the end. Brian, if you get the number of nodes, then add one more node to it. So Brian, if in order to find the end of the last node, you would need to traverse the entire list, unless, as Adrian pointed out, unless you're keeping track of tail, which a lot of lists do. A lot of lists will, you have with your data structure. So here for our array, right, we keep track. We have our actual array, which is going to be this this array of elements. But then we have these things like capacity and count, which is metadata. So for linked lists, you often store the head. Well, the head you always store, and then you have the tail, and then the tail makes it easy to add to the end. So if you're storing the tail, then it's a big O of 1 to add to the end. But otherwise, you would have to walk through the entire list. Just because it's big O of 1 to add to the last elements of a linked list, of a singly linked list, it's no matter what big O of n to add to the second to last element of a singly linked list, right? Because I don't think any implementation will store the tail and then also the second to last tail, unless I guess you specifically design it to do so. So yeah, and adding to the front is going to be big O of 1 for a singly linked list, which is very nice. Doubly linked lists are nice because then you always have the head and the tail, and then you have efficient ways to access from either direction. What is the big O of adding an element to the beginning and end of array in JavaScript? Exactly the same as we described here in that are described here in these slides. JavaScript works just like Python. So keep these in mind. Keep these in mind. Same with strings. Strings are just arrays underneath the hood. It's just character arrays. So all of these array functions work the same for strings. How is the big O? Okay, we talked about this. Are we revisiting arrays? What are they? I really hope that this question is answered. Why are we revisiting arrays? Because these are super important. And I think, like, hearing all these questions, I'm very encouraged that this is something that we need to go through. If anything, if you take anything away from computer science, from your entire 10 weeks in CS, it's going to be, if it's up to me, it would be this. It would be remember how arrays work, okay? Because you're going to use them so many times, and they can be really, really, really inefficient if you use them wrong. Look at this. Just adding from the beginning instead of the end is the difference between less than 1/10 of a second and over 50 seconds, right? And this is something so unintuitive, right? Like if you just looked at this before looking under the hood, would you know which one is faster? It doesn't really you can't really tell, right? So this is why we study big O. 500,000 isn't even a lot. 500,000 seems like a lot, but what do you have? Like, if you have 500,000 followers on Instagram, like, what is that? You're a C-list celebrity, a D-list celebrity, right? So in computer science and coding, you're going to come up with numbers a lot bigger than 500,000 quite often. And if you have code that runs in 50 seconds, that's no one's going to wait 50 seconds for your code to run. So you want to be doing things in the most efficient way possible. And in order to do that, you want to be thinking about the memory underneath the hood. And it's not just with arrays. Like, it's with all of your data structures. Like, the reason we study data structures is because sometimes there's more efficient ways to do this. If you're searching through your array a lot to find values, if you're doing that, that's the O of n operation. but maybe you want to sort it, right? Maybe you want to keep it sorted so you can go from O of n to O of log of n, which will give you a huge boost. This is the most important practical takeaway, I think, of computer science. Understanding what's going on with this code. Yeah, I think this will help you write better code and more like what'll happen. Like you're gonna write some code and it's gonna be really slow and you're not gonna know why, right? Why is my code running slow? We need to speed it up. You can start looking through your code and you'll start to see, the way you make code more efficient is you can just like run through it. It'll be like, all right, adding, addition, subtraction, multiplication, that's all going to be constant. You can't really make that more efficient. Anytime you see a for loop, okay, what's going on in this for loop? This is going to be an O of n, right? Take some time to look at what's going on in that for loop. Do you have any n operations inside of that for loop? Because then you're going to get n of n squared, right? And then sometimes you can identify things like array operations, adding to an array. That's a candidate for something that can be slowing down. String operations, that's another candidate for something that can be slowing it down. There's a ton of different culprits, and this gives you the tools to be able to look at your code and evaluate piece by piece exactly what's going on at each line. All data structures. I don't know if I would go so far as to say all data structures. Like a linked list doesn't use an array, although I suppose you can think of a linked list as like a 2-element array, where the first element is going to be a value and the second element is going to be a pointer. But things like binary trees are usually implemented as arrays, where your first one is going to be. I think you studied how to do the calculation where the index is going to be like this to the power of whatever degree it is, and then its neighbor is going to be that plus 1. So you can use, again, since arrays are the most efficient way to store something, that's a good way of storing stuff. If you remember that memory is just a string of infinite tape. So it's like a one-dimensional array. It's a one-dimensional strip of tape. So again, the best way to store stuff all in one space is going to be in an array. So that's why Adrian, that's why most of it's pretty commonly stored as that way, because it's just the most efficient way without having to jump everywhere in memory. And that's why things like structs are all stored. It's all stored not as an array, but in a contiguous block of memory. Arrays specifically are all the same type. And the reason that they're all stored, they all have to be the same type, is because that lets you access different indices. Ooh, Sean is typing. Sean has some thoughts to add, maybe. How does JavaScript calculate each element address in the array if elements in the array are of different types? I said I would get back to this, and I think we'll revisit this after you've done a little bit of your homework. But again, the way it does this is using pointers. So in Python, everything is an object, right? In Python, everything is an object, and everything has an address. So even integers you think of as a data type, not an object, but integers have addresses too. So if you do like ID of 1, 2, 3, you'll see it has this address in memory. If we do x equals 1, 2.0, 3, 4, 5, 6. So this is an integer, a float, a string, a list, and a dictionary. These are all different types. But actually what it's storing is a pointer to each type. So this is an array of pointers. And this is a pointer to an integer. This is a pointer to a float. This is a pointer to a string. This is a pointer to a list. And this is a pointer to a dictionary. So each of those pointers is going to be the same size. So that's how mixed typing works. But great question. Same in Python, same in JavaScript. Are there instances where you don't have to declare the size of an array? How does that work? So you can do that in high-level languages because high-level languages allow you to resize arrays dynamically. So so if you do something like x equals this and then x dot append 1, 2, 3, you don't need to declare it as size 3 at the beginning because it's resizing dynamically. Underneath the hood, it is declaring these sizes, which you can see. Let's see, which you can see here. So 64 is the declared size of the empty string. 96 is, or is this with one item? I forget. This is with one item in it, 2 items in it, 3 items, 4 items. Let me see. What is it? Size of empty array? It's not size of. Sys get size of. Sys get size of empty array 64. Okay, so I guess 1, 2, 3. Okay, so that's interesting. When you append, it makes stuff bigger than when you just declare it like this initially. I'm assuming C also stores struct as an array of pointers, like mixed type Python lists. Okay, we have 5 minutes left. All right, so here's the deal. I got a comment that that students, since there's brown bags that come up at 11, that a lot of that people like to are worried about missing stuff if I go over. So I think I don't want you to miss stuff. So so it's fine so I'm going to try to not go over anything that's like mandatory after 2 o'clock, but I will keep going after 2 because I know that some people like to get the extra help and extra questions. So I'm going to keep going, but feel free to dip out at so it's 2 o'clock for me. So feel free to dip out at 11 if you want to jump into the brown bag, or if you have something at 11. You can always come back to refer to the lecture video afterwards if you need. But yeah, I'm still gonna keep going. Go over one of the homework problems with some pseudocode for a good example. Okay, as far as the homework, I wrote instead of pseudocode, I wrote some lines. Now these are pretty good descriptions, I think. So basically, what you want to do is take each of these comments and fill out the lines of code. Sometimes it's going to be like how do you allocate memory for an array struct? This should be pretty easy. I'll go over this. Do like array star array equals malloc size of array, right? So that's this. And since you want to return an array, return array. So that's pretty easy. You can say array dot capacity equals capacity array dot count starts with 0 and allocate memories for elements. So this is going to be the tricky one. So array elements is a char star star. You're right, R. So use calloc capacity and size of char star. Okay, so what calloc does is it allocates the memory and then it sets all the values to 0, which you're going to want to use which is just helpful. I'm not sure if you might not actually need to do that here. You could just malloc capacity times size of char star, but like this is basically what you want to do for creating an array. Allocate the values, set your defaults here, and allocate the memory for this. Destroying is going to be pretty much the same, except for you need to free every time you do malloc. And the way you know what you need to free is that every time you've called malloc, you need to call free. One gotcha here is that if you've assigned any strings to this array already, you're going to need to free all of the strings inside of the array also. All right. C also stores structs as an array of pointers, mixed type Python lists. No, C, you need to specify the type. C, you need to explicitly specify the type. So here, we're only storing character pointers to car stars, and these car stars are like strings. So these can only point to character stars. If you wanted to make it a mixed type, you would need to do something like objects like this, and then you would need to define object, and then object would have a different type, and it's kind of a mess in C because there's no inheritance. There's no strict inheritance, but there's some tricks that let you do object-oriented style inheritance in C. But I think that's out of the scope of what we're trying to do. This stuff is it Python? Which one did you run? Is this the front and the back? Celia? Add to front and add to back. So is this saying that both of these ended the same? Okay, that's interesting. I wonder why. Maybe they run it differently than mine. Yeah, I wonder. I'll try that out myself, but I know that on my computer that this code runs in 50 seconds. I'll try running it and see if I can figure out what's going on there, Cecilia. Are there any questions that I want to? Okay, we're almost done with these questions. Why do we need to declare the size of an array? That's what we went over that in C. You need to declare the size of your array because everything needs to be side by side. And then you request this memory, and then some other stuff happens, and then some other memory might be taken up here, so and then here and here, and then when you want to request more, you can't grow this array because there's already some stuff here. So you're going to need to request a new block that's slightly bigger. Largest number you can request in 4 byte, represent in 4 bytes, 4 billion or 2 to the 32nd power. Deeper recap on big O of n measurements. Hopefully some of the stuff we went over helped you out with this. It's helped you out with this big O of n stuff. Remember, if we're doing stuff n times, then it's big O of n. So even though we have something like add to front, this looks like just a single line. It's still doing an n operation because you need to scoot n things over. All right. Well, we actually ended up pretty well on time. Are there any other questions? Let me try running. Celia, can you post the link to this thing? I have it somewhere, but I don't remember. And yeah, feel free to dip out if you want to check out this brown bag. Awesome. I was glad to hear. I like it too. I like it a lot more too. I feel a lot more interactive. Like I get to hear what's going on with you guys instead of just asking questions and hearing crickets. All right, let's try this. Python tutor. So first we will put in this code. And then we will put in this code. Oops. Right, and visualize execution. EOL while scanning string. Oh, these are made it curlies. Why did just that one become a curly? It's weird. Okay. Oh gosh, 99. Can we just step to the last? Instruction limit reached. Okay, that makes sense that the instruction limit is reached. How did you get a Cecilia? How did you get these runtimes without defining add to back and add to front? Cecilia, are you still there? All right. I mean, where did these definitions like add to back and add to front? Like here, I define them up here, add to back and add to front. But how does this program know what these functions are? You're only importing time, so I don't. Oh, I see. You did add to back equals. So you did add to back equals. So you're just setting these variables equal to 500,000. So you're not running this 500,000 times. So these are functions. Remember? So this is an add to back function, and it takes in 500,000 as a variable. So so the reason that it's happening in constant time is that you're not actually running these functions. You're just setting something equals. So so there's no equal sign here. All right. Phew. Okay. Big O still stands. Still works. I'm glad. All right. This is all right. So good stuff. Any last minute questions about the homework before I let you all go? Again, destroy array should be pretty simple. Just mirror this. Make sure that you also before you free your elements array, make sure you walk through it and free every element inside of it. That's one gotcha. And read should be pretty easy. Read should be only a few lines of code. And append I think is going to be where most of the work is done. But also append is not too tricky either. If you get done with this early, I highly recommend that you start working on things like insert and delete, because those will take a little bit more. You're going to have to implement the scoot methods that we talked about in lecture and in the video. All right. Well, if there's nothing else, I guess I'll let you go. This is a one-day project. This is a two-day project. So let's see. Good question. All right. So part one is day one. I guess I should call this day one instead of part one. So this is day one. Day two is insert, delete, and resize. If you finish these, then you can fill out the rest of Python methods for stretch goals. Or you can move on to the second part, which is going to be hash tables. So day one, what MVP for today would be implementing create, read, destroy, and append. And I already did create for you, so this should be pretty easy. Hopefully it should be pretty easy. I know nothing is easy in C, so hopefully you'll be able to make it through. All right. Thanks for listening, everyone. Thanks for bearing with this new our new schedule. It seems to be working well. I like it a lot. Give me feedback if you hate it. Let me know if you like it. You can also let me know. Otherwise, I will see you all tomorrow. Thanks. It's great to be back.